Hello and welcome to this lecture. In this lecture, we are going to solve the first order ODE that you get for an RC circuit with an AC source. So this involves a little bit more computation. So let me go through this in some detail. So what do we have here? We have an AC source. Okay, my picture is really bad here. I shouldn't have this picture. Okay, so anyway, let me live with this picture. This picture seems to show a DC source. It's actually not a DC source. It's phi sine omega TV. Okay, so it is like I should have a different picture here, which has an AC source here. Apologies for that. But anyway, this AC source at time t equal to 0, the switch is turned on and it starts flowing into the RC circuit, RC. So this has, you'll see, strikingly different behavior than the DC circuit. You can imagine this is AC circuit, so it will have a different behavior. And we know the equation, no? We saw this equation before, I prime of t plus 1 by RC I of t equals 5 omega by R cos omega t. So this is the equation. And from here you can identify this is a first order ODE. It's a first order ODE, p equals 1 by RC, this is a constant, but then q of t becomes this complicated function, trigonometric function, phi omega by R cos omega t. Okay, so how are we going to approach this? So if you look at e power pt times q of t, you have phi omega by R, this is a constant, that's okay. And then you have e power t by RC times cos omega t. Okay, we have not seen this kind of function before. E power t by RC, exponential t by RC multiplied by cos omega t. Okay, so this is the complicated looking function that we have, and somehow we have to find an antiderivative for it. How do we find an antiderivative? That is the essence of this problem. That's what makes this problem slightly more complicated than the previous one. So this involves a bit of calculation. So let's see how we do that. Okay, so this takes a little bit of effort. Let me just quickly go through it. So e power pt times cos omega t. I'm going to write cos omega t in terms of the complex exponential. Notice how complex numbers enter the picture. So in a way you're learning trigonometric function, exponential function, complex exponential, complex numbers. So complex numbers enter the picture and really help you. Okay, so here is cos omega t e power I omega t plus e power minus I omega t by 2. Now I can multiply through, I'll get half e power p plus I omega times t plus e power p minus I omega times t. Okay, now I can do an antiderivative. I can do a complex antiderivative. It's just complex integral, complex exponential, and this has got a okay. So this is just a sum of two exponentials, and we can do an antiderivative for this, right? The antiderivative for this is half times e power p plus I omega t divided by p plus I omega plus e power p minus I omega t divided by p minus I omega. I am almost treating this p plus I omega like it were a real number, okay, real constant. Okay, so that's okay. These things work out. We have not seen this in great detail, but anyway, these things work out. You can obviously, hopefully believe me when I say the complex numbers also work like this. Okay, so now this I can simplify, right? So I can take multiply the denominator out. I'll get p square plus omega square. Do you see that? P plus I omega into p minus I omega is p square plus omega square, right? So this is how it works. And then p plus I omega will come here, p minus I omega will come here. After some simplification, okay, so I hope you can see that p plus I omega into p minus I omega will give you p square plus omega square, 1 by 2 is still there. And in the numerator, I am going to take e power pt common outside. Okay, so this e power pt is going to come out, just like it went in here, it's going to come out. I will have e power pt, but then what I will have left here is p minus I omega times e power. So maybe I should just show this real quick for you. Okay, so e power p plus I omega times t by p plus I omega plus e power p minus I omega times t by p minus I omega. Okay, so I'm doing a lot of things at the same time. So I'm first taking a constant out, the multiplying the denominator. I'm just doing this addition. So in the numerator, I'm taking e power pt common outside, and then I will have p minus I omega times e power I omega t plus p plus I omega times e power minus I omega t. Okay, so this is just the same thing. I mean, if you multiply e power pt throughout, you will get the same thing again, right? So it's this exact same thing. Now this product, I can write it as, p times e power I omega t, p times e power minus I omega t. I'll take p common out here. I'll get plus e power minus I omega t. And then I have an I omega. I'll take the minus I omega common out. I'll get e power I omega t minus e power minus I omega t. Okay, and then denominator p plus I omega into p minus I omega is p square plus omega square. This is all that has been done here. Okay, so I hope you can see this. So I've done that to get this form. Okay, so now again identify e power I omega t plus e power minus I omega t is cos. E power I omega t minus e power minus I omega t, I'll get sine, right? So I'm going to use that here. So this becomes e power pt by p square plus omega square. This 2 will go in here. I'll get p times cos omega t, right? Minus I omega times, again the 2 comes here, and this I know is 2i sin omega t, 2 and 2 will cancel, I'll get I sin omega t, okay, as simple as that. Next simplification, okay, you have to do a little bit of simplification to get to the answer. So I'm going to write this same thing in a slightly different way, okay. So p square plus omega square, we're going to write as square root of p square plus omega square into another square root of p square plus omega square. You'll see why we are doing this. Eventually we'll get to a very, very nice and simple form, I promise you that, but let's stay with me. So this root of p square plus omega square alone we'll send inside, the other things we'll keep here. So once you do that, you get this nice form where you have p by root of p square plus omega square cos omega t plus, where did I get a plus here? I into I is I squared is minus 1, minus of minus 1 is plus 1, plus omega by square root of p square plus omega square sin omega t. Now this guy inside the bracket looks to be very, very complicated, but actually it is a very simple thing. What I can do is, what I have here, p by square root of p square plus omega square is actually sine of some angle, right? If you have a right angle triangle with p as the opposite side, omega as the adjacent side and phi as that angle, hypotenuse is square root of p square plus omega square. So sin phi is p by square root of p square plus omega square. Cos phi is omega by square root of p square plus omega square. And you can also write tan phi to be p by omega. Much simpler form, right? Tan phi is p by omega. So if you do that, you get this very nice form where you have this e power pt by square root of p square plus omega square hanging along, but then you have sin phi cos omega t plus cos phi sin omega t. What is sin a cos b plus cos a sin b? Sin a plus b. So you have the antiderivative of e power pt cos omega t to be this very, very simple form, which is e power pt sin omega t plus phi by square root of p square plus omega square, and where tan phi is p by omega. Okay. So that is the final antiderivative calculation. It involved a little bit of calculation, but finally the answer is really, really simple. E power pt cos omega t, the antiderivative, let me just go through, do I want cos omega t? Yes, I want cos omega t. Okay. So e power pt cos omega t, the antiderivative is e power pt sin omega t plus phi divided by root of p square plus omega square. Very, very nice and simple expression, and there are a lot of reasons why it has to be of this form, and that form is very, very useful to us. So finally, we can now solve the RC circuit with AC source. Why is that? Because this is our equation, this is P 1 by RC, and this is my Q of t, and e power pt Q of t is phi omega by r. This is just a constant. I have e power pt cos omega t, and I know the antiderivative for this guy. Antiderivative for this guy is phi omega by r will come along, and then instead of this, I will have e power pt by square root of p square plus omega square. What is p? 1 by rc. So 1 by rc square by omega plus omega square sin omega t plus phi. Okay. Now in circuits world, this is written very differently than this. Okay. So what people would do is, they'll define something called impedance, which is actually r plus 1 by I omega c, and then tan phi. What is tan phi? Tan phi is p by omega, right? P by omega, p is just 1 by rc, so 1 by omega rc. So these two you define, you know phi. This z is very, very useful. So what happens here, you notice this expression, right? I have here omega by r root of 1 by rc squared plus omega square, right? So what I will do is, I will write this as 1 by square root of, right? So this r by omega will come, and then r square by omega square will go inside, right? Times 1 by r square c square plus omega square. Okay. So this whole thing will become 1 by square root of 1 by omega square c square plus r square. Okay. So this, if you see, if z is r plus 1 by I omega c, then this guy is just equal to absolute value of c, magnitude of c, right? Square root of r square plus 1 by omega square c square. So this is a very nice simplification. So I have this omega by r square root of this guy, and that whole thing just becomes 1 by mod c. So I can write this complicated, slightly complicated looking antiderivative as 5 e power t by RC divided by mod z, where z is this, just this parameter sine omega t plus phi. Okay. So, this is the form which is nicest for describing AC circuit currents and voltages. Okay. So, I of t now becomes phi by z sine this guy, right. So, this is the antiderivative multiplied by e power minus pt. So, if you multiply by e power minus t by RC, this will cancel. So, you just get phi by z sine omega t plus phi plus c times e power minus t by RC. Okay. So, now comes the question on the initial condition. Initial condition turns out for this circuit I of 0 is 0. Okay. So, you may say previously I put I of 0 as phi by r. How did I get 0 here? That is because sine omega t, right. At t equal to 0, the voltage is 0. At t equal to 0, nothing really happens in the circuit. Voltage is 0, capacitor has no voltage, no current will flow. So, I of 0 is 0. So, if you do that, you will end up getting minus phi by mod c sine phi for c, right. So, you just put t equals 0 here, you will get this value. So, finally, the entire solution looks like this. The current I of t in an RC circuit with an AC source which is turned on at t equal to 0 is phi by mod c sine omega t plus phi minus sine phi times e power minus t by RC. So, there is a transient part, there is a part here which will go off to 0 for large t, okay, with the time constant RC, and there is a part here which is not going to vanish. Okay. For the first time we are getting something like this, right. Even if t goes really large, this part will still remain, no, sine omega t plus phi. Okay. So, let us see this interesting little answer in the plot of the solution. If you plot the solution, here is the entire plot. I will walk you through this slowly. I have I of t which is phi by mod c into sine omega t plus phi minus sine phi e power minus t by RC. Now, infinity, I infinity of t, right. If I send t to infinity, what happens? This part will go off to 0, but this part will remain, it will not go anywhere. So, at infinite time also I always get this kind of an expression, it will never die out. As long as I have my AC source, I will keep getting an AC current throughout the circuit, phi by mod c sine omega t plus phi. Okay. And how quickly does it get there? That depends on the time constant. Okay. So, here are the plots of the three things. I have plotted I infinity of t, which is the first part of this equation, right, phi by mod c into sine omega t plus phi. I have also plotted in green this part alone. Okay. So, this part, second part alone, right, phi by mod c sine phi times e power minus t by RC, that is this. What will be the actual I of t? The difference of these two, right, that is the black curve. Okay. So, you see here I infinity is the blue curve, blue dotted curve. This other transient term, this is called the transient term, something that dies out for large t is called the transient term. The transient term is this green dots, and the difference of these two is the actual current I of t. So, you see the I of t is trying to catch up with I infinity of t. It really wants to go to I infinity of t. This transient part is what is stopping it, and as the transient part dies down, this I of t gently but surely goes slowly and steadily to the I infinity of t. See, by the time it finishes like 1 cycle, 2 cycles, it has already hit. You see the blue dot and the black line are right on top of each other, it has already hit it. What are these black dots? These are the time constant. Okay, this is the 1 RC, the 2 RC, the 3 RC. By the time it comes to 3 RC itself, you see that the blue dots are on top of the black curve and steady state has been reached. So, this is called steady state when you have large t where the transient has died down, you only have the steady state left, and you already see that the current is quickly getting to the steady state. So, this is a nice illustration of what happens when you solve the first order ODE corresponding to a RC circuit with an AC source. Thank you very much.